Um, Welcome all to this talk. And today I will be speaking on the use of satellite data in an operational NWP data assimilation system. So this is basically what we are doing in India, National Center for Medium Range Weather Forecasting, NCMRWF, under the Ministry of Earth Sciences. And before going to the talk, I will give an overview of the different modeling system that we are using in our center. So as you know that global operational centers, they receive the global observations from different sources. Similar to that at NCMRWF, we are also receiving almost all the global observation in near real time, like observation from low Earth orbit satellite, geostationary, aircraft, radio sonde, means all the in situ and remote sensing observation we are receiving. And we do the observation processing and the quality control and the data assimilation. We have both deterministic and ensemble system, both global and regional over the Indian domain. And then after that, the data assimilation, then the forecast model, then the post-processing and the product generation for our different users in different sector. So this is the, basically we have an MOU with Met Office, UK Met Office. So our model is based numerical weather prediction system, and we have the high resolution global deterministic NWP system that we call as NCUMG, that is the NCMRWF Global. And we have twice daily 10 days forecast from this global system, and the global resolution is 12 kilometer. And we have a regional system based on NCUM, that is the resolution of 4 kilometer, and we used to give 3 days forecast from this regional system. And during winter time, we run 2 days forecast based on 330-meter resolution model over Delhi region. It is mainly for the fog forecast. And we use the hybrid 4D assimilation for both global and regional deterministic system. And the use of global observation is on par with the leading NWP centers. We do compare with the observation usage at NCMRWF and ECMWF regularly. And now what we noticed is initially some 5 years back, there was a huge gap between NCMRWF and ECMWF data utilization, but now we are getting almost all the data from through GTS, then through NOVA and through UMETcast also. So the data observation usage is on par with other global leading operational centers. And apart from the deterministic system, we have the high resolution global ensemble system also. So our ensemble resolution is also 12 kilometer, and we use 22 members and one control, that total 23 members, and 10-day forecast we give. And these forecasts are available in the TIGI portal. And we were running regional high resolution ensemble forecast system, but currently we are not running operationally. And atmosphere, land, ocean, sea, ice coupled system is used for sub-seasonal and seasonal forecast. This is based on this system, we give 1 month forecast every Thursday and 3 months seasonal forecast in every month. And we also have a reanalysis. This is the regional reanalysis over the Indian region. This is 42 years high resolution regional reanalysis produced using the system. And we also have a global reanalysis based on the GFS system. And that is for 20 years from 1999 to 2018. And this is our modeling system. So we have the 12 kilometer global model, then 4 kilometer regional model, and we have one more 1.5 kilometer regional model also. Then the 330-meter Delhi model. This one we run only during winter season for the fog prediction. And we have the global ensemble prediction system, regional ensemble prediction system, and the coupled model that we are running with very coarse resolution, that is of 60 kilometer. So now coming to the talk, the outline is, this is mainly the use of satellite data in the operational system. So how do we monitor the satellite microwave data at NCMRWF, then the forecast impact, and what is the India's contribution in the past, present, and what will be in the future, and active microwave instruments like scatterometers, and what is the current status of that spatial gap analysis of different satellite equator crossing time, and the summary. So the monitoring, so we have the microwave instruments used in NCMRWF assimilation system. We use EDOS, and onboard NOVA and METOP satellite. And the sources we are getting this from NOVA and ISDA, NewMedcast, IMD, INCOIS, and NRSC. So INCOIS and NRSC, we are getting the regional the DBNet data, and the ATMS from NPP and NOVA 20, that is again through NOVA and STIS we are getting. AMSR2 on board GCOM W1, again through NOVA and STIS and UMedcast. And similarly, these are the satellite. It is already used in all the global leading operational system. And if we see Saphir is the humidity sounder, microwave humidity sounder on board Megatropics. And last January, that means 2022 January, this mission life was over, and it is now not operational. And recently, last 10th of February 2023, ISRO launched another humidity sounder. This is an experimental that launch. It is the millimeter wave humidity sensor, and the satellite is Microsat 2B, and it is the ISRO called this as EOS 7, that is the Earth Observing Satellite Series 7. And this is again an experimental mission, and the expected life period is 1 year. And then we assimilate the scatterometer winds also. So this millimeter wave humidity sensor data, ISRO has not yet started disseminating operationally, but we got some sample data. We are doing some experiment with that. And this is the coverage during different assimilation cycles. So you can, this particularly I put the coverage over the India, whenever we are having passes over the Indian region. So the top panel shows the passes from different instruments during 0 and 12 VZ assimilation cycle, and the bottom panel shows during 6 and 18 assimilation cycles. So this, I already told that we are getting the DBNet data from 2 stations over India. So apart from this, we were getting some of the DBNet data through GTS also, that from Australia, Korea, Japan, and Hong Kong. And we were having 3 DBNet stations over India, that is Chennai, Delhi, and Guwahati. But these 3 stations are not working now. And we means access the data through the level 0 data from INCOIS and NRSC, and we are processing this data at NCMRWF and disseminating the same through GTS. And this is the coverage of DBNet data we receive from the 2 stations over India. So this is the ETOS, and the top panel is ETOS, and the bottom panel is the ATMS data. So this is the monitoring. So how do we monitor this observation? So we do the monitoring, the bias, standard deviation, and the count number of observation it is assimilated in each assimilation cycle. This is for METOP 1 ETOS, the O-B background innovation. So here the red circle shows the 15-day, last 15-day mean, and the blue one shows the daily mean, that day particular assimilation cycle mean. So here we can see that some circles are very big. So these channels we are not assimilating in our system. And others are, we can see that the bias is almost the 0 line. This is for ETOS. So then here also we can see for AMSU A and AMSU B. AMSU B channels, the bias is slightly high. The standard deviation is slightly high, but still it is maybe 1 Kelvin kind of thing. So similarly, this is for another instrument, ATMS. We have ATMS on 2 satellite, SNPP and NOVA 20. So this is again bias, standard deviation, and count. So here we can notice that the count from NOVA 20 is higher than the count from the SNPP, because in our assimilation system, we have given the priority to NOVA 20 than the NPP. So this is the forecast impact that we are doing. So this is for 4 years, 2019, 20, 21, and 22. So during 2020, we can see the impact of that pandemic also. So that almost all, except the satellite observation, other conventional observation, that impact was less, because of particularly if you see the aircraft and all, during 2020 and 2021 the impact was less, and 2022 it was slightly picking up, but it was not up to the mark to the 2009. Here that I put arrows mainly for the microwave instruments ETOS. So the maximum contribution is from ETOS, but we have ETOS from many satellite, NOVA series and METOP series satellite. Next is ATMS, that is again from 2 satellites, SNPP and NOVA 20. Then we have AMSR, that is again single satellite GCOM W1, then GMI, onboard GPM, and SSMIS, then FI3D, then Saphir. Saphir, if you see that we were having only during 2019 and 20. After that, it was very irregular. It was that impact was very less. And MWRI and FI3P and FI3C. If you see the FI3 series of satellite, that is the CMA satellite, we are not having access to the full data set. So because of that, the impact is very less. We are getting only only a small patch of data through the DBNet services. So then coming to the India's contribution to the microwave side, the means humidity sensor. So the first contribution, we can see the Megatropics. It is a joint Indo-French satellite. It was launched by ISRO on 12th October 2011. And it is the speciality of this one is it is positioned in a highly inclined equatorial plane of 20 degree at a height of 867 kilometer above the Earth, so as to orbit the tropical region between 30 degrees south and 30 degree north, nearly 14 to 15 times per day. And if we see, there were 4 payloads in this satellite: one microwave radiometer Madras, microwave humidity sounder Saphir, radiation budget instrument Skyrab, and a radio occultation sounder Rosa. But unfortunately, the microwave radiometer stopped working 2 months post launch, and the Saphir is one of the most used data by all the global leading operational centers, and many centers, they reported the positive impact of Saphir in the NWP system, mainly from NSUB, ECMWF, then Met Office, Meteo France, and NCMRWF. Almost all the global centers, they reported the positive impact. So here in this one, we can see this left right side figure is the opacity spectrum. So here if we see, so there are 2 water vapor bands, that is one is in the 20 gigahertz region and one is in the 183 gigahertz region. And these Saphir channels are in the 183 gigahertz region because it peaks very high in the atmosphere. So here this left panel shows a comparison of 183 gigahertz channel in different instruments like MHS, Saphir, and ATMS. So one speciality what we noticed in Saphir is the
Ma'am, you
Saphir
have
lowest
3 more minutes now.
Okay, lowest peaking channel, so it has more impact, and we have the positive impact of this Saphir also. So when we did some super instrument, like we since the Madras it stopped working, we combined the MSR2 and Saphir, and what we noticed is when we combine the imager and sounder, we get the maximum benefit, that in the lower atmosphere the imager will be performing better, and in the upper atmosphere the sounder will be performing better. And this is again the comparison. If you see 2018, from single instrument MT Saphir, we were getting 3.5% error reduction in the short range forecast. But if you see 2019, 20 and 21, it is reduced because the instrument become unstable, and the data also very much discontinued that time. And the follow-on mission by the ISRO, that is that I already told, that is the microsat 2B. But if you see the difference between these two, that this microsat 2B is in a very low altitude, that is around 450 kilometer. And we have seen that channel difference, the frequency difference also. This second column shows the microsat 2B M2B MHS channel frequencies, and the last column shows the Saphir frequencies. And we saw that the M2B channels are slightly pushed downward, and that we can see in the that weighting function also. So this dotted line is for Saphir and the continuous line is for the microsat 2B. So for all the channels, we can see that pushing down of that particular channel in the microsat 2B. So this is the gap in the spectrometer wind. So we have analyzed the gap. So we saw that during 0 UTC and 12 UTC, there is a gap over the Indian Ocean region. And we can see that only 6 and 18 UTC, we were having the current spectrometer coverage over the Indian Ocean region. And there is another mission by OceanSat ISRO, that is OceanSat 3, but again the spectrometer data has not means disseminated operationally. So this is the gap analysis, spatial gap analysis we have done in terms of the equatorial crossing time. So here we can see that we can see a huge gap in the 6 and 18 UTC. But if you see the 0 and this that yellow dotted line, you can see that is the 0 and 12 UTC line. So 0 and 12 UTC around plus or minus 3, we have many satellite observation, but in the 6 and 18 UTC, we have gap. So this is the summary. So we regularly monitor the all the observation we are getting and process and assimilate the observation, and microwave radiance helps to reduce 30 to 30% of error reduction in the 24-hour forecast. That is the combined effect. And megatropic Saphir was one of the most highly used microwave humidity sensor by leading global operational NWP senders. And as a follow-on mission, ISRO launched an experimental satellite that is in the 37-degree inclination at an altitude of 450 kilometer compared to the 20-degree inclination of the megatropics and 867 altitude of the megatropic orbit. This is slightly different. That is a 37-degree inclination, so it may cover more than 30 degrees south and 30-degree north. And it is in a very low altitude, 450 kilometer. With the expected life period is 1 year, but it can extend. And NCMRWF is working on the assimilation of these radiances and the scatterometer gap and the radiance gap in the 6 and 18 UTC. And active microwave instruments in the early morning and afternoon orbits are essential for the NWP system, particularly during the extreme weather events. Then we have FI3E, but NCMRWF don't have access to the FI3E data. So here I will stop. Thank you for your attention.
Thank you, ma'am. So now we have a question from Rakesh. How do humidity sounder in Safir help in improving convective system forecast over tropics?
Yeah, actually, that specific convective system we have not done, but we have done some assimilation during cyclones. So then cyclones, what we have seen is because mainly the lowest peaking channel of that Saphir, it helped to improve the means simulating the improved that intensity and the track also. But specific to convective system, we have not done because we have done all these experiment in our global system.
Okay, next question is from Florian Mayer. Are you running variational bias correction in your systems?
Yes, we are running the variational bias correction.
Yeah, thank you, ma'am. And one more question is here from Steve Elvers. Are you able to obtain microphysical or precipitation information from the microwave satellite radiances?
Microphysical and precipitation.
Microphysical or precipitation information from the microwave satellite radiances.
Means specifically what we have seen is due to the assimilation of Saphir, it improved the precipitation mainly during the spin-up time.
Yeah,
Otherwise,
actually, yeah,
specifically, we are not
yes.
retrieving.
Yeah, actually, I maybe I can give the answer. Actually, this microwave channels are also used for the retrieval of precipitation. Okay, so now last question from Dr. Xavier. Do you do any chemical data assimilation from satellites?
No, right now we are not doing, but in our other system, that is the GFS system, that is mainly for IMD. So we are doing the ozone assimilation. Otherwise, in the UM system, we are not doing.
Okay, actually, okay, I think now we don't have any other question. Okay, so uh, one more question is recently there. Swapnan Malik is there. Uh, for radiance assimilation, is clear sky only or all sky radiance assimilation is
Yeah,
including?
microwave, we are using that ARMS, ETOS, ARMS-UA and MHS all sky assimilation, but all other radiances, microwave radiances, we are clear sky only.
Okay, thank you very much, ma'am. And actually, one last question from my side.
Okay.
So, to utilize this DVNet data, are you presently using the continuous data assimilation as a operational system?
Yes, we are using.
Okay, thank you very much, ma'am. So now we have a next
Thank you.
presentation from Anika